third speaker this morning is Andrzej Derdzinski from Ohio State University, and he's going to speak about Riemannian Yang-Mills connections in four manifolds.
Thank you. First, I would like to thank the organizers for putting this wonderful session together and for inviting me. This is a presentation of some results, some work still in progress, joint with Paolo Piccione. The idea is to look at the condition of harmonic curvature and with a particular emphasis on dimension 4. We're looking at four-dimensional Riemannian manifolds with harmonic curvature. And it turns out that we can largely reduce the question of understanding their structure in the compact four-dimensional case to a problem in real algebraic geometry, and I will present this reduction and also outline some steps already achieved in this reduction itself. So first of all, this is related to Yang-Mills connections very strongly because the condition of harmonicity of the curvature, which means that the divergence of the curvature tensor vanishes identically, means the same as requiring that the Levi-Civita connection of the metric in question be a critical point of the Yang-Mills functional. The Yang-Mills functional operates on connections compatible with a given metric. I'm talking in this case about connections in the tangent bundle, which do not have to be torsion-free. The metric is fixed. We are looking at connections preserving the metric, and with each such connection, we associate the L2 norm squared of the curvature tensor. The integration is with respect to the volume element of the metric. So critical points of this functional, which when the critical point happens to be the Levi-Civita connection of the metric in question, if and only if the metric in question has harmonic curvature. An additional feature of this Yang-Mills functional, which is related to its physical origins, is that in dimension 4, it is conformal invariant for very obvious dimensional reasons. So we are looking first at the examples of Riemannian four manifolds with harmonic curvature. Let me once again point out what this means. It means in local coordinates that this expression is zero. In other words, the divergence of the curvature tensor vanishes. And because this divergence is generally equal to what we would call the exterior derivative of the Ricci tensor, this is a consequence of the second Bianchi identity, the harmonicity condition imposed on the curvature amounts to requiring the Ricci tensor of the given metric to be a Codazzi tensor, in other words, to satisfy this Codazzi equation. So let me now point out some examples in dimension 4. What kind of compact examples are already known? First of all, we have the class of compact four-dimensional Einstein manifolds. Then we can consider conformally flat manifolds with constant scalar curvature. They automatically have harmonic curvature in any dimension. Then there are the locally reducible examples. In dimension 4, those will be the cases of the factor dimensions 1 and 3 or 2 and 2. And finally, there is a class of non-trivial 2 plus 2 dimensional local Lord products, which I'll mention in more detail. Right now, let me point out some general context here. If you consider the Schouten tensor of a given Riemannian metric, which is the Ricci tensor minus plus a specific multiple of the scalar curvature times the metric, and then you form, as usual, the Weil conformal tensor in dimensions starting from 3, then we have these identities, the Bianchi identity for the Ricci tensor, saying that the divergence of the Ricci tensor is 1/2 of the differential of the scalar curvature, and then another identity which follows from the second Bianchi identity is that says that the divergence of the Weil tensor is a specific dimension-depending multiple of the exterior derivative of the Schouten tensor. What this means for our purposes is that every metric with harmonic curvature necessarily has constant scalar curvature because of this identity here. And secondly, in dimensions starting from 4, harmonicity of the curvature is the same as requiring harmonicity of a Weyl tensor and simultaneously constancy of the scalar curvature. In dimension 3, we don't have that for the following reason. The Weyl tensor is automatically equal to 0 for algebraic reasons. However, the condition of conformal flatness in dimension 3 is equivalent to requiring that the exterior derivative of the Schouten tensor be identical to 0, this expression be identical to 0, that the Schouten tensor be a Kodacki tensor field, and then in dimension 3, harmonicity of the curvature means precisely the same as requiring the metric to be conformally flat and have constant scalar curvature, with this meaning of conformal flatness encoded in the Kodacki equation imposed on the Schouten tensor. Now, so this, in other words, these general facts explain why Einstein manifolds are automatically examples with harmonic curvature, simply because they have a parallel Ricci tensor, and therefore the Ricci tensor satisfies the Kodacki equation. Similarly, conformal flatness with constant scalar curvature implies harmonic curvature because in particular it implies vanishing of the divergence of the Weyl tensor, and we have constancy of the curvature, which gives us this. And finally, because the condition is expressed in terms of the curvature, it is invariant under Cartesian products, and therefore we have the class of locally reducible examples, which means manifolds that are locally Cartesian products of lower dimensional manifolds with harmonic curvature. In lower dimensions, we know what this is. In dimension 1, everything has harmonic curvature. In dimension 2, it means constancy of the Gaussian curvature. In dimension 3, it means conformal flatness with constant scalar curvature. And finally, there's this class of non-trivial 2 plus 2 warped products, which I would like to mention now. But first, let me scroll down through a few pages and concentrate here on the second paragraph. Let's ignore the beginning of this page. So we are looking at the following situation. There's a closed surface, and we are considering a bundle of two spheres with a structure group SO3. We can think of it as the unit sphere bundle of a vector bundle of fiber dimension 3 with a fixed fiber metric. And we want this bundle to be flat. In other words, we want this bundle to carry a fixed flat SO3 connection. So once you have a flat bundle of two spheres over this given closed surface, you can fix a metric on the surface and pull it back to the horizontal distribution, and also consider on the fibers a fixed metric of constant Gaussian curvature, say C, invariant under parallel transports. And locally, the picture is that of a product manifold, because it's a flat bundle, so you form a product metric. In other words, you form this vertical metric I mentioned of constant Gaussian curvature C, and on the horizontal distribution, you pull back the metric from the surface. Then once you have this locally product metric on the total space, you change it conformally, globally, by essentially dividing it by the square of its scalar curvature. So this is the formula which appears here in the notes a little earlier. Namely, we take this product metric here. I'm writing it like this, but I mean what I just said, the product metric obtained using the flat connection and the geometry of the fibers. Here is the product metric. Here is up to a factor of 2. This will be the scalar curvature of the product metric, the sum of the Gaussian curvatures of this base surface and of the constant Gaussian curvature C of the fiber, the two-dimensional sphere. We divide this metric by the square of the scalar curvature, assuming that this expression K plus C, that this scalar curvature of the product metric is positive everywhere. So this makes sense. And this metric then will necessarily have harmonic curvature, provided that such a nonlinear elliptic equation is satisfied on the original closed surface by its fixed metric. So what this equation means is really constancy of the scalar curvature of the conformally rated metric, because the metric, the product metric here in this case, will automatically have harmonic vowel tensor. So the harmonic curvature condition amounts to constancy of the scalar curvature, and this is the expression saying that the scalar curvature is constant, that up to a factor of this constant here is the scalar curvature of the conformally related metric. So again, we are looking for the case of a closed Riemannian surface with Gaussian curvature K. We wanted non-constant, otherwise we get trivial product examples. We want the Gaussian curvature to be non-constant. We also want the presence of two constants, C and R. They both have to be positive, such that K plus C is positive everywhere on the surface as well. R is a positive constant, and we have this nonlinear second-order elliptic equation imposed on the Gaussian curvature. Once this equation is satisfied and the Gaussian curvature is non-constant, the resulting flat two-sphere bundle over our closed surface Q with this metric will be another example of a metric with harmonic curvature. A metric which is, as you see, a word product, because we're dividing a product metric by a functional factor which is constant along this factor manifold. So it's really a word product metric of dimensions 2 plus 2. Now, let me point out something else here. When you carry out this construction, the metrics which you obtain will not be Einstein or conformal flat or locally reducible of type 2 plus 2. However, it may happen that the metric resulting from this construction is locally reducible of type 1 plus 3. So even though we obtain it as a non-trivial word product of factor dimensions 2 plus 2, in some cases it turns out to be also a product, locally a product metric of factor dimensions 1 and 3. This will occur only when this surface we start with is homeomorphic to the torus or the Klein bottle. This is the only possibility that may occur, and there are actually explicit examples showing that this situation may occur. What do we know about the existence of examples constructed in this way? In other words, what do we know about the possibility of having this condition satisfied along with positivity of some K plus C, non-constancy of the Gaussian curvature K, and again, this condition satisfied with positive constant C and R on a closed Riemannian surface with some suitably chosen metric. Now, it turns out that there are some existence results here which are obtained by applying a bifurcation argument. In other words, we can start from a constant curvature metric and deform it, obtaining a curve of metrics with the property I just named. And that works on the sphere as well as on the real projective plane, giving us an uncountable family of such examples. It also worked on closed orientable surfaces of genera greater than 1. As I mentioned before, solutions to that nonlinear elliptic equation with non-constant Gaussian curvature can also be produced on the Klein bottle and the torus, but the only solutions we have found in this way are metrics which in dimension 4 after the conformal change turn out to be locally reducible, so they're not interesting from our point of view. In any case, this class of 2 plus 2 word products, or in other words, flat two-sphere bundles over closed surfaces, has plenty of examples which are known to exist within it, and the whole discussion of this class is totally reduced to finding closed surfaces satisfying this equation with non-constant Gaussian curvature K, such that K plus this positive constant C is positive everywhere. In other words, we can say that this is one of the cases which can be swept under the rug in the sense of being reduced to something otherwise familiar. The class of Einstein manifolds in dimension 4 is very far from being understood, but it's otherwise familiar, so we leave it aside. Similarly, for conformally flat manifolds of constant scalar curvature. By the way, constancy of the scalar curvature, of course, is achieved here always by a conformal change starting from conformal flatness due to the solution of the Yamabe problem, the case which was solved by Shane. The locally reducible cases, another separate familiar story. And then we have this fourth class of otherwise familiar examples, those flat two-sphere bundles over closed surfaces. So So we are now asking the question, is there anything beyond these four types of examples? And so we start a discussion of examples other than these four classes. So first of all, it's convenient to introduce these invariants. This lowercase boldface r is the number of distinct eigenvalues of the Ricci tensor, or more precisely, the highest such value of the number of distinct eigenvalues, the highest value achieved anywhere in the manifold. And I'm assuming the manifold is oriented, and I'm considering also the invariance w plus minus, which is, each of them is respectively the highest number of distinct eigenvalues of the self-dual Weyl tensor or anti-self-dual Weyl tensor, which operate as endomorphisms in the bundles of self-dual or anti-self-dual bivectors. So metrics with harmonic curvature are automatically real analytic in suitable local coordinates. That's a theorem due to de Turck and Goldschmidt, and therefore both of these maximum values will be attained simultaneously in some dense open subset of the manifold. In addition, what happens is that if you exclude the Einstein case, in other words, if you assume that this invariant R is greater than 1, then W plus and W minus, those two invariants are actually equal, because W plus, the self-dual Weyl tensor, has at every point the same spectrum as the anti-self-dual Weyl tensor. And so from now on, assuming that this is the non-Einstein case, W can be 1, 2, or 3. I'm using the symbol W for the common value of these two invariants. So what happens? When W is 1, that means the conformally flat case, because those tensors W plus, W minus are traceless. So if such a tensor has just one eigenvalue, it means it's 0. W equal to 2, it turns out that this leads to the case where the metric is obtained as I described on a flat bundle of two spheres over a closed surface, precisely by that construction, which means from now on this case can also be left aside, and so we're left with a situation where W is equal to 3. Both the self-dual and anti-self-dual Weyl tensors at all points of our open dense subset have 3 distinct eigenvalues, and I'm also excluding the Einstein case. So next, one can show by a tedious but elementary argument that this, again, aside from known examples, in the compact case, this Ricci tensor then necessarily will have 4 distinct eigenvalues, but I'm getting a little bit ahead with the story, so let me first concentrate on what we do next. So we can pick a trivialization of the tangent bundle of the manifold by orthonormal analytic vector fields. Again, we are doing this either locally in our open dense set, or possibly we can do it in every connected component of that open dense set, replacing it if necessary with some finite covering. So we pick those orthonormal analytic vector fields which simultaneously diagonalize the Ricci tensor or the Weyl tensor, or if you like, they diagonalize the curvature tensor. And that means that whenever you have two pairs of indices, such that the first set, ij, is different from the second set, then the corresponding component of the Weyl tensor is 0. Equivalent, it says, this property means that the exterior products of our orthonormal vectors at every point form eigen vectors or eigenforms, eigenbivectors of the Weyl tensor acting on bivectors. So such a frame always exists, and it's essentially unique up to changing signs in those individual orthonormal vector fields. So we pick such orthonormal analytic vector fields which sometimes diagonalize the Weyl tensor and the Ricci tensor. And then what happens next is we have to look more closely at the connection components relative to such an orthonormal frame. More precisely, what we concentrate on are 3-element subsets, say a subset ijk of this set of indices 1, 2, 3, 4, and we're asking when such a subset can realize a non-zero connection component. When can you choose an order of ij and k in this 3-element subset so that this component, this inner product, is non-zero somewhere in your manifold? What is the number of these 3-element subsets which realize a non-zero mixed, I would say, component of the Levi-Civita connection? It turns out that this number, for algebraic reasons related to the condition of harmonic curvature, cannot be 3 or 4. You cannot have, the number of such sets a priori can be between 0 and 4, but you cannot have 3 or 4 at all. The possible values of this are 2, 1, or 0. In other words, the number of 3-element sets of indices from this range 1, 2, 3, 4, which, under appropriate order, realizes a non-vanishing connection component. There may be 2 of them, or 1 of them, or none of them. And then, if there are 2 of them or 1 of them, we can understand the situation completely. In the case where there are 2 of them, compactness is excluded. Actually, completeness of the manifold does not occur. And the reason is that when you have 2 such components, they give rise to a totally geodesic 2-dimensional foliation spanned by a couple of these vector fields from our orthonormal system. And then you can look at a global function such as the length squared of the Ricci tensor, and it satisfies along each geodesic tangent to the 2-dimensional distribution a certain ordinary differential equation which implies that it blows up in finite time. Such a manifold cannot be complete. I'm using analyticity of such metrics to draw such a conclusion. Once you have this equation on some interval of the parameters for your geodesic, it will be satisfied on the whole geodesic as long as the geodesic is complete, and therefore thus such a geodesic cannot be complete. Secondly, if d is equal to 1, if there is only one 3-element set which gives rise to non-zero connection components, looking at it more closely, you realize that this is locally reducible. There will be one of those vector fields, E1, E2, E3, E4, will actually be parallel. So we are left only with the case d equal to 0. There are no mixed connection components. The covariant derivative of EI, of EJ in direction of EI, where I and J are different, is a combination of EI and EJ. And because it's orthogonal to EJ, it's really a functional multiple of EI for every pair IJ of different indices. So that's the only case which is left. In other words, if d sub I denotes the directional derivative along this unit vector of EI, then we have a bunch of differential equations. I'm writing them, they're written down here. We don't need to pay much attention to them. Here is the property that there are no mixed components of the Lev-Jita connection relative to this frame, for instance. Del sub EIJ, when I and J are equal if FJI EI. In all these formulas, when 2 indices appear, such as IJ, KL, 2 or more of them, they're automatically assumed distinct. So that means for any distinct IJ, we have such a relation with some functions. Then, of course, we get this, we get the Lie bracket components, and then we have derivatives of the eigenvalue functions for the Weil tensor and eigenvalue functions for the traces Ricci tensor. They are controlled because of these equations which express separately vanishing of the divergence of the Weil tensor and the Kodacki equation for the Ricci tensor. There are also further conditions which are imposed on the certain directional derivatives of those connection component functions. Those conditions come from the fact that the curvature tensor is diagonalized by our frame. So we have a bunch of equations which look quite unpleasant, but we can handle them to some extent. There are algebraic relations here, for instance, expressing symmetries of the Weil tensor and the fact that these are the eigenvalues of the traces part of the Weil tensor. And then it is convenient to introduce certain new objects. For instance, using the connection components, these connection component functions, which at any point form a 4x4 matrix with zeros on the diagonal. So it's out of them we form quadratically a certain system of numbers at any given point. So it's a certain system of functions. We can also encode it as a function valued in off-diagonal 4x4 matrices, and we can also, from the eigenvalue functions of the Weil tensor and those of the traces Ricci tensor, we can build bilinearly a certain system of functions. The reason why these functions are important here is that you can think they satisfy a certain additional system of equations. You see, those differential equations, the large number of differential equations I wrote previously, they do not control all the directional derivatives. For instance, the directional derivatives of these f's, the connection components, are only controlled in special cases when all three indices are different, or in such a case where you have an expression for a curvature component in terms of the connection component. So all the other directional derivatives are fully controlled. The system is solved for the first-order directional derivatives of the sigmas and the lambdas, but not of all the f's. However, what happens is that you can still apply further differentiations to those equations, and in some cases, it produces integrability conditions, the form of algebraic relations imposed on these functions. In particular, we get this integrability condition. These h's, the functions h, which are built quadratically from the connection components, along with these functions, the z's, which are built bilinearly from the eigenfunctions of the traces, Ricci, and the Weil tensors, together, they obey this system of bilinear conditions, which may be expressed that if you think of them as matrices, this is a diagonal matrix, that's an off-diagonal matrix, and the product is skew-symmetric. Now, if you look at this system and differentiate it further, you get more algebraic relations. More and more algebraic relations seems to generate those algebraic relations almost for free, with one exception. You see, when this h happens to be 0 identically, then this equation says that 0 is equal to 0, and all the algebraic consequences will simply say that 0 is equal to 0 in that case, which means the case where the functions j are all identical to 0 has to be isolated and dismissed off separately, because in that case we get no conclusions. But when h is not identical to 0 and some of these components are non-zero somewhere, we can restrict our open-dense set and require that those components are non-zero to be non-zero everywhere, and then we can proceed further with differentiating this system, getting more and more of those algebraic conditions, which eventually lead us to a system, to a new system, enriching that system, a new system in which all the directional derivatives of all the components of f in all directions will be controlled. Although, and unlike this system where they are controlled by polynomial functions of the original unknowns, they'll be controlled by some homogeneous rational functions, which means our control is incomplete because we have to look at the denominators of those rational functions and separately consider the case where the denominator is identical to 0. When the denominator is not identical to 0, we have a system solved for all the derivatives, and we can just happily generate further and further integrability conditions, which will all be algebraic conditions imposed on these unknown functions. And we have looked at this through a certain number of steps, and they all seem to generate further and further independent conditions, which means we are far from knowing exactly what the full answer is, but the situation is more or less like this, that yes, after we have 24 exceptions, 24 derivatives that are not controlled, but once they are controlled in a manner I described before, assuming that h is not identical to 0, we end up reducing the number of unknowns. Specifically, if we start from the original unknowns, there will be 18 of them, 18 variables, the components of the lambdas, the sigmas, the f's, and the scalar curvature, which even though it's constant, may conveniently be treated as an extra variable. There are 18 variables on which we keep imposing more and more algebraic relations. We know that if we impose the first 6 of them, the dimension will actually drop to 12, assuming that h is not identical to 0. And then what else happens is that the first 6 equations here don't involve the scalar curvature, so we can leave it alone, pretend it's not there. And there will be really 17 variables forming a variety of dimensions 17 minus 6, which is 11. But then these equations are tri-homogeneous, separately homogeneous of a specific degree in all the 3 kinds of variables, the lambdas, the sigmas, and the f's, which means we can projectivize them since all of these variables form non-zero vectors. And the effective dimension drops to 8. We're looking at some subset of a product of 3 real projective spaces. So this is a very promising line of argument which we are still working on, reducing this system of equations for reducing the number of the actual independent unknowns further and further, we hope to conclude in this case that the set of solutions is either geometrically trivial or something very, very narrow. But let me, instead of elaborating on this further, let me mention this step that I mentioned was necessary. You see that what I just said is summarized here. This is tri-homogeneous, the system 12. H depends on the connection components F quadratica. Z depends on the eigenvalue functions bilinearly. So it's really, if you think of it as imposed on the triple lambda sigma H, is tri-homogeneous, separately homogeneous in each of them. They may be assumed non-zero, lambda and sigma. If H is non-zero as well, the projectivization of in each of those three variables reduce the dimension to 8. In other words, this triple of functions takes values in a variety, in an 8-dimensional variety, algebraic variety, sitting in a product of real projective spaces, and there it satisfies a bunch of further algebraic equations. So we would like to understand further what these equations tell us, and our basic conjecture is that they tell us there is nothing there other than the examples already known. In other words, since the examples already known have been excluded, there is really nothing there. But the case H equal to 0 has to be isolated and separated because all of these procedures of generating further equations only work when H is not 0. When H is identical to 0, whatever we get reads 0 equals 0. So let's consider the case where H is equal to 0. And it's really convenient to make it more general because all of this discussion makes sense in more generality, even though it's not derived in the same way. So more general situations like this. Let the manifold be just anything, of any dimension n greater than 2, 4. Let's assume that we have trivialization of the tangent bundle by orthonormal vector fields satisfying these Lie bracket relations with some functions f, I, j. Let's assume that this manifold has harmonic curvature and that the Ricci tensor has these orthonormal vector fields also diagonalize the Ricci tensor, which has n distinct eigenvalue functions at every point. These are the eigenvalues of the Ricci tensor. And let's assume that H is equal to 0, identical, that this connection component function, these components of the Lie bracket will turn out to be, of course, the same as the components of the Levi-Civita connection, that these connection components or the Lie bracket component functions, the structure functions of this trivializing system satisfy this family of homogeneous quadratic equations. That's the case H equal to 0. So we're just looking at the higher dimension because it turns out that for the discussion, much of the discussion, this doesn't make any difference and it's just more natural and even simpler notationally if the dimension is arbitrary. So what happens is that this leads to two subcases, very natural, generic and non-generic. I define the generic case like this, but it's equivalent, which I didn't have time to add to the notes. It's equivalent to saying that one of these components for some pair A, ij is not identical to 0. That's the generic subcase. So if not, the generic subcase means again that each of these, sorry, did I say identical 0? It means every one of these components for every pair ij is non-zero somewhere. None of the components is identical. So this is a generic case. I probably misstated it. So in the generic case, it turns out that we can draw a lot of conclusions. We can get a system of equations satisfied by these component functions with some constant c. And there are some new functions present in these equations, those phis, but they are also subject to equations which control the derivatives, the directional derivatives in all directions. The equations are nasty, but it's even worse than it looks because this is the equation for the directional derivative of phi I in direction of I, but it uses a selected index j different from I. It seems the right-hand side seems to depend on the choice of j different from I. This is what our equation, our geometric problem dictates to us. This condition, this equality is really that's the equation imposed on the rigid tensor, written in this language, which means the right-hand side has an extra symmetry. It doesn't depend on how you chose j different from I, and this doesn't depend. That's why this doesn't depend, and that means you can forget the differential equation and simply write that symmetry condition, and that will be a system of algebraic equations. You see, the fact that this remains the same, the right-hand side, when instead of j different from your I, you fix another index k different from your I, the fact that this remains the same is a system of linear algebraic equations imposed on the functions phi with the coefficients that depend generally the coefficients involving the variables. The coefficients of the matrix are linear in the f's, and the right-hand side is quadratic in the f's. So you get this system of equations, algebraic equations. This time we generate further and further equations. This system is very heavily overdetermined, and it looks like we still have to work out the final details, but it looks like this overdetermined system does not have solutions. More precisely, you find solutions of a weaker system that this system implies, and then when you plug them into the original differential equation, you get a contradiction. So what happens is that the generic case does not occur, and therefore we're only left with a non-generic subcase, which means, again, that besides, in addition to this system of equations, the connection components satisfy the condition that one of those functions, for some indices ij, fij is identical to 0. Turns out that this looks like nothing because there's a bunch of these functions, n times n minus 1 functions, f sub ij. One of them is identical to 0. However, this system of equations causes that vanishing to spread like plague through the whole system. And it turns out that if you have one of these components vanishing, there will be many, many more. What happens is that there will necessarily exist a decomposition of the index set 1 through n into two non-empty disjoint subsets, P and Q, such that whenever the first index is from P and the second index from Q, this component will be 0. Now, if you look at what these Fij are, that was a while ago, you see the fact that all these say that all these Fij will be 0 when I is from the first and j from the second set, it means that the vector fields from the first set will be parallel along those from the second set. In other words, let me go back to that page. It means that if we form the distribution spanned by the vector fields corresponding to the second set of indices, then the first span of the triangle complement of the distribution will be parallel along it, which means this distribution has totally geodesic leaves. So we also have something like this. We have this very powerful bit of geometric information, distribution with totally geodesic leaves. But then more happens, namely, you can take this decomposition, which automatically exists in our non-degenerate case, and make it maximal. Replace this decomposition with one in which the set Q is maximal, for which there is no such other decomposition whose analog of Q contains this one, Q, this Q as a proper subset. If you make it maximal and look at what happens, then there is not just this total geodesic distribution, but its orthogonal complement is totally umbilical, and if you look more closely, it's a work product. You get a work product decomposition, a work product with harmonic curvature. Now, people have looked at work products with harmonic curvature all the time since the 1970s. There are various formulas, various expressions. Generally, the problem is not completely understood. It's far from being well understood because except when the total geodesic factor is of dimension 1 or 2, the equations are unpleasant and are not understood. So people don't know what these work products of harmonic curvature are. But in our case, we end up with a characterization of when such a work product metric has harmonic curvature. So what happens in our situation? In our situation, we're going back to dimension 4. The first, the total geodesic factor could be of dimension 1, 2, or 3. When it's of dimension 1, we know it implies conformal flatness in dimension 4. When it's of dimension 2, it implies we are in this class of flat two-sphere bundles. And finally, we're left with a geodesic factor of dimension 3, which we don't understand. What we know is that this is the case of a singular work product. In other words, our work product manifold is not globally a product manifold. There's a manifold with boundary. You take its Cartesian product with a circle, a three-dimensional manifold with boundary, take its Cartesian product with a circle, and then those circles over the boundary points are shrunk to individual points. So you get a singular work product, and this singular work product is still subject to some conditions, such as this: the Ricci minus the Hessian of the warping function divided by warping function should be called that tensor. And this condition will become simplified. It says that this tensor here should have divergence 0. And so this is where we are right now, and we hope to understand some more about this work product situation. And I guess I'm out of time, so I'll stop here. Thank you.